So we've just seen a couple examples, and in our first example that we did with the geometric series, we found that for certain values of x, it was going to converge, others was going to diverge. For our second example, we had some it was converging, some it was diverging, and we had to check the endpoints to make sure. And then in exercise 7, it was always converging. And it turns out that there's actually 3 possibilities for any given power series. First one is that the series converges only when, x is equal to a. So if you think about it, when x is equal to a, this makes all terms equal to 0 except the first. Because every single thing is just a minus a, so that's 0 to whatever power. 0 to the 0 power is undefined, so this is a little bit weird as to what exactly it would converge to, but it would in fact converge. You really just have your leading entry there. Option 2, the series converges for all x. And this is what we saw in the exercise above. So that's like exercise 7. And then option 3, there's a positive number r, such that the series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. And this is like we saw in exercise 6, which we had the x plus 3, absolute value of x plus 3 less than 1 is when it converged. Our a value was -3, and the 1 there was our r. This type of r is called a radius of convergence. It's telling you how far from the center you can go and still converge. So in this case, we can go a distance of 1 from -3. That's why it was between -4 and -2. In this case, case 1, that's up here, if you're only converging when x is equal to a, we would say that your radius of convergence is 0. And in case 2, when you're converging for all values of x, we would say your radius of convergence is infinity. And for option 3, you would have an actual number for your radius of convergence, like 1 or 2 or 7. The interval of convergence is the interval in which this series converges. It may include the endpoints, and it may not. So it does give us slightly different information than the radius of convergence. And I have this remark here. When finding the interval of convergence of a power series, you first find the radius of convergence, and this gives you a preliminary interval, a distance from the center. But then you always have to check the endpoints of the interval as well to see if they work in the original power series. Occasionally you have something that's like a geometric series and you can tell, but you would still need to check those endpoints. So let's do example 8. So this is the geometric series we saw before. Remember, this is sum to infinity n equals 0, x over 2 to the n. So it converges if the absolute value of x is less than 2. That implies that our radius of convergence is equal to 2. And our interval equals -2, is less than x is less than 2. So everything between -2 and 2 could be in our interval. And the question is, what about this or equal to? Right? Could it be equal to -2 or could it be equal to +2? So let's check the endpoints. At x equals -2, I'm plugging -2 in for x, and I'm getting the sum of -1 to the n to infinity, starting at n equals 0. And this is going to be like 1 minus 1 plus 1 minus 1, etc. that diverges because it oscillates. So it's always going to be 1 or 0, and then 1 or 0 when you add up the partial sums. It's never going to settle down. And at x equals 2, you get the sum to infinity starting at n equals 0 of just 1 to the n. But of course, 1 to the n is just 1. So you're just adding up 1 plus 1 plus 1. And that's, of course, going to diverge because it goes to infinity. So in this case, our interval of convergence is equal to all the x values from -2 to 2, but not equaling -2 or 2. And we usually actually write this in interval notation as -2, 2, not to be confused with the coordinate -2, 2. These are all x values from -2 to 2. And remember, the parentheses means you don't include the point, whereas brackets would be including the point. So like, I think in this example up here, I would write it as -4 with the bracket and -2 with the parentheses, if I wanted that to write the interval there. All right, let's summarize what we have so far. For that one we just looked at, our radius of convergence was 2, and the interval of convergence was -2 to 2. For this previous example with the x plus 3 to the n, our radius of convergence was 1, and our interval of convergence, that was one we just looked at, is from -4 to -2. The -4 is included and the -2 is not. And then for this crazy-ass looking one, our radius of convergence was infinity, and our interval was -infinity to infinity because it's all values of x. So go ahead and pause the video now and try to calculate the radius and interval of convergence for the series in exercise 9. So pause the video now, try that out. So once again, we are always going to start by doing the ratio test. And when we do that, on top, our a sub n plus 1 is n plus 1 to the n plus 1, and then x plus 5 to the n plus 1. And here we can actually write it as a normal fraction because we don't have a fraction within a fraction. We get n to the n on the bottom over times x plus 5 to the n. Of course, taking the absolute value of that. And let's see what happens. I'm going to take this top thing. I'm going to factor out an n plus 1. And the reason I'm doing that is that I'm now left with an n plus 1 to the n, which I can divide by my n to the n. And they have the same exponent, so I can combine them. For the x plus 5s, I've got n of them here, and then the other n are going to cancel there. And I'll just be left with an x plus 5. That'll be in the numerator. So what happens to this thing right here? Well, we take the limit as n goes to infinity. This thing right here is going to turn into an n plus 1 over n to the n. And this thing here is getting closer and closer to 1, and the n is getting closer to infinity. And you might remember that in fact is an indeterminate form from way back when you were doing, I guess it was L'Hopital's rule. It turns out that what this actually converges to, if you fool around with it or do some research, is it's the same thing as 1 plus 1 over n to the n, which you might recognize as n goes to infinity. That's equal to the number e. It turns out, though, this doesn't really matter because what's happening to the n plus 1, that thing's going to infinity. And so this thing here, it's either going to be going to 1 or to infinity, or to some number in between, but the n plus 1 is definitely going to infinity. It doesn't really matter what the x value is. This whole thing is going to go to infinity. So the limit as n goes to infinity of I'll say n plus 1 times 1 plus 1 over n to the n times x plus 5. It's going to equal infinity unless, what's the one situation for our unless? Unless x equals negative 5. Because if x equals negative 5, then what we've got here, that would always be 0. And that would cancel everything out. So, or I could have said that x plus 5 is equal to 0. So what do we have? Our radius of convergence is equal to 0. This is a situation where it almost never converges. And our interval of convergence is just the point x equals 5. And the way we write that, there's two ways. You can either use curly brackets set notation to just say 5, or you would use, negative 5. You would use square bracket negative 5, comma negative 5. So you're including the negative 5, but that's it. And that would be my answer for exercise 9.